All right, well, I'm going to try a problem now that we're going to be working with disjoint and independent events. And I want to see if, I can prove whether these events are disjoint or whether they're independent. Got a trademark here. Don't mind that. I'm just going to get rid of it or else I'm going to try. It's going to work. Let's see. Let's try it now. Cool. All right. So I know the probability of A. I know the probability of B. And I know the probability of A and not B. So there are a couple of ways I can work through this. I'm going to show you using a Venn diagram first. And that's kind of my preferred method. But, two-way tables work for a lot of people, so we can also try that. I'm going to show you using a Venn diagram. So I create my sample space using my rectangle. I'm going to create a circle for event A and event B. Now, remember, this area in the middle here is where they overlap, where both are happening at the same time. So right now, I know the probability of not A and not B happening is 0.42. So that's going to go right outside my circle here. So I'll keep writing in black here. So what that tells me is that when I'm adding up the probabilities of A and B, right, based on what they're telling me here, I should be getting an answer, probability of A or B should be 0.58. And I know that because probably neither event happening is 0.42, which means everything in those circles should be adding up to 0.58. Now, I know that the probability of A is 0.3. So that means this whole circle here has to add up to 0.3. Now, notice it includes that overlap. So I'm not going to just blindly say that it has to be 0.3 right here. I'm not saying that. What I'm saying is that everything right here has to add up to 0.3. So I'm going to have to do a little bit of work here. Oops. So now, if that it's telling me probability of A is 0.3, probability of B is 0.4. Okay. That's telling me everything in here is supposed to add up to 0.4. Probability of everything in here is supposed to add up to 0.3. And you'll notice that I'm getting some overlap here. Notice how I colored something twice in the middle? That's telling me something's getting counted twice. So right now, I'm doing the probability of A plus the probability of B. I'm getting 0.7. I'm supposed to be getting, though, 0.58 right here. See, I'm supposed to be getting 0.58 because the probability of neither happening is 0.42. What that's telling me is that I'm counting something twice when this is happening. That 0.3, that's supposed to include some of this overlap. That 0.4, that's supposed to include some of this overlap. So here's what I like to do. I'm going to add up what I've gotten for probability A and probability B. I'm getting 0.7. I'm going to take away that 0.58 because that's what's supposed to be there. When that's telling me is that 0.12 is getting counted twice. That's going to be this overlap here. So I can figure out the overlap, which is really cool. That overlap right here is going to be 0.12. Now, what I can use now is I can use that to figure out the probabilities of A and B alone. Because since I've already accounted for that overlap, and the probability of A is 0.3, I take away the probability of both happening at the same time, that amount that was counted twice, I get 0.18. And likewise, if I do the probability of B, which is 0.4, subtract the probability of them both happening at the same time, 0.12, I get 0.28. If I add all these up, 0.18 plus 0.12 plus 0.28, I get 0.58, which makes sense because as you'll see right here, 0.42, that's the probability of it not happening at all. So if I add those up, I get 1, which is what I want for my sample space. Based on what I'm seeing here, let's see if I can answer this question. Are these events disjoint? They are not. Here's the reason why. Disjoint or mutually exclusive means they can't happen at the same time, which means there should be no overlap. I should be getting 0 right there in the middle. That's not happening. We already established when they're giving me that 0.3 for probability of A, 0.4 for the probability of B, stuff's getting counted twice. So that's that 0.12. So I know it's not disjoint. So I can get rid of disjoint here. I can get rid of this and get rid of this. So I'm down to A and B. Now, how do I prove independence? There are a couple of ways I can do this. I'm going to show you both of them. One way I can do it is the probability of A times the probability of B should give me the probability of both of them happening at the same time. Let's see how my math works out. Probability of A is 0.3. I'm going to erase that, excuse me. Times 0.4. That's probability of B. It should be giving me 0.12, the probability of them both happening at the same time. Look what happens here. Probability of them both happening at the same time. That is 0.12. That proves independence to me, because probability of one of them happening times the probability of the other one happening, they will equal the probability of them both happening if they are independent. That's happening here. That's kind of cool. Another way I can prove this. Take a look at the probability of A. Probability of A is 0.3. What should be happening is the probability of A doesn't change if I look only within B happening. Here's what I mean by that. I look just within my B circle here, right? I've got everything in that B circle here, right? Everything here. That gives me 0.4. So that would be my denominator. Within that 0.4, everything in B, how often is A happening? 0.12. So now the way I can prove independence is if I do 0.12 divided by 4. Let's do that. Notice how I'm getting, oh, I should have done it. My decimals are off. Let's look at 0.12 divided by 0.4. Notice how I'm getting 0.3. That's awesome. That should be happening. What that's telling me is that the probability of A doesn't change. It's still 0.3 while I'm just looking at that subgroup of B. So when I'm looking within B, I'm looking how often probability of A is happening within B. It's still 0.3. That's great. That's another way of proving independence. So I've proven independence, and I've proven that they're not disjoint. I've done that using a Venn diagram. I'm also going to show you using a table, because some people like using tables. So I'm going to show you how you can do this using a two-way table as well. I'm going to tuck away my Venn diagram. Now, the goal when doing these is that you're following along with the problem. Maybe you're trying it yourself, and you can do the thought process along with me. So I do a table here. Oh, that's a bell, no big deal. We're not going anywhere. Probability of A, probability of B. We're going to go with yes, no, yes, and no, just like so. Probability of A happening is 0.3. So all my yeses right here should be adding up to 0.3. All my yeses for B here should be adding up to 0.4, excuse me. And the probability of neither happening is 0.42. So that's going to go right here where both my no's are. So hopefully you're following where I'm getting these. Yeah, I want the probability of A happening is 0.3. So I just went right here into the yes column. Everything in the yes column should have to 0.3. Everything in my B column that's yes should have to 0.4. That's where that's coming from. And then I worked with my no. The probability of neither happening is 0.42. What I can do now is I can kind of work backwards a little bit. I know these all have to add up to 1. It's my sample space. It always adds up to 100% or 1. So then I can work backwards a little bit here. I can fill in this value. 1 minus 0.4 is 0.6, which tells me the probability of B not happening is 0.6. I can also figure out the probability of A not happening. 1 minus 0.3 gives me 0.7. Using this, I can start filling in some values. 0.6 minus 0.42 gives me 0.18, which is the probability of A happening, the probability of B not happening. I can work backwards a little bit here too. 0.3 minus 0.18 will give me 0.12, the probability of yes and yes, probability of A and B happening. And then I could do 0.4 minus 0.12 to give me a probability of B happening, but A not happening. 0.28. There are a lot of ways you can do this using a table. I think you might have even thought to yourself, I would have subtracted in a different order. That's fine. The goal is that you're working with the unknowns to find these unknown values. Now that I have this stuff, I can still answer these questions. Disjoint means not happening at the same time. It's definitely not happening. It's probability of them both happening at the same time is 0.12 according to my table. That's great. Independence, again, I can use the same formula I did last time. Probability of A times the probability of B. equals the probability of A and B happening at the same time. Those values haven't changed. I still have 0.3 and 0.4. Multiply them and get the probability of them both happening at the same time, 0.12. That's independence. I can also go with probability of A happening is 0.3. And then if I look just within B, right, just within B, which is 0.4, probability of A happening within B is 0.12 over 0.4, which gives me, once again, 0.3. So I've proven independence. These are two different ways you can do it, using a Venn diagram or a table. Either way is fine. Whatever modality works best for you. Again, I was a Venn diagram guy up until recently, and now, I mean, I like using tables too. So I'd say try both of them, see which way works best for you. But these questions aren't bad. What you just got to remember is fill in what you know, and then you'll have to plug in some unknowns. But tables can help with that, and Venn diagrams.